trends we're going to talk about are the ones from your assignment. So if you finished the assignment yesterday, that's fine. Maybe you want to just take a look after we do the concepts here. So when you have atomic size or atomic radius, it's the same thing. We often think of atoms, especially if you think of them like boarded as perfect orbits, then it's very circular. So where it's, and circles have a radius, right? The distance from its center to the outer boundary. This says, so the nucleus, which is the center, approximate outer boundary. So this is sort of leading into the idea that an atom is not perfect. Okay, that there's like this probable electron cloud. That's why it says approximate. Oh, it even says cloud-like. So we'll talk more about the real ideas behind atoms next year, but it's more or less what we need to do with it. It's going to work. Okay, so if you think of an atom like a circle, then the radius is the distance from the nucleus to the outside. So we're going to, in every single trend, we're going to talk about how it's affected across and up and down. Okay, so we'll go down first, because moving down a periodic table for most of the trends has a bigger effect than going across. And the biggest reason behind it is when you go down, you get more energy shells. So especially in this one, when the atomic radius is going to increase going down, which makes perfect sense because you're going to have more energy shells. So you can write energy shells, energy levels, orbits, whatever term makes more sense to you. And we talked yesterday about how not only do you get more orbits, you also get shields as well, blocking the positive pull of the nucleus. And sometimes people will say, well, don't you also get more electrons and protons? Doesn't that pull the nucleus in, or the electrons in closer to the nucleus? But these two ideas, these 2 points, are so much more important than the increase in the number of electrons that we say it overrides it. So even though we are getting more protons, which we defined yesterday as nuclear charge, then it's the fact that there are more energy levels and shields, then that is a greater effect than the increasing number of protons and electrons. Okay, Okay, so then up and down is not a big deal. But when we consider going across, to keep it sort of the same, because we're English readers, we start at the left usually when we talk about how it's the trend's affected, and then go to the right. Okay, so it says going across, it does say left to right. So a period is a row. So now we're in either row 1 or row 2. So this time there is no more energy levels or energy shells. They have the same. So if you're in the same period, the elements are going to get smaller or the atoms, because that's now we have the same number of energy shells, but you're getting more protons, more electrons, so you get more attraction. So we did define nuclear charge yesterday. If you want to add in here, the number of protons, you can, because the definition was on a different slide, whatever's going to make sense to you. Okay, so the number of protons increases, increasing the attraction, pulling the electrons in closer, and we're not getting any more shields, no more energy levels. That stays the same. Okay, so when you have an ion, again, the unfortunate weight analogy sort of works here. If an atom gains electrons, it gets bigger. So yes, you can think of it like, gaining weight, that gets bigger. You gain something, you get bigger. But the atomic reason is when you get more electrons, that means that now you've got an uneven number, right? When we made an ion, so now you've got more electrons than protons, and then electrons are like, and they will repel each other. And when they repel each other, it gets bigger. So more repulsion is created, and they move slightly further apart. So then the reverse is true. If an atom loses, then the volume is going to decrease because there's less repulsion. Now we have more protons and electrons. They can pull them in. They can be attracted. And this has implications for other topics in chemistry as well. When we start to look at the structure, so if you have a metal and a nonmetal, like an ionic bond or an ionic compound, then within their structure, it's actually crystalline or like a repeating pattern, and you can calculate the distance between the anion and the cation, and the cation is smaller and the anion is bigger. So that affects how they fit together. It affects whether it's going to dissolve in water or not, like whether you get a precipitate or solid form. So there's lots of implications of these trends, not just about which is bigger, which is smaller, etc. Okay, so for ionization energy, there's a little bit of a definition about what energy means in science. So if energy is required to do something, then that's not a good thing. Atoms, molecules, compounds, they don't want to waste energy. So if a lot of energy is required for a reaction or whatever, then we would consider that to be non-spontaneous. Whereas if energy is released, then that's a good thing. That is considered to be spontaneous. So for ionization energy, just look for a second, okay? So this is sodium. Sorry, so here, not that this isn't in your note because you don't need to memorize this. The sodium atom is 186 picometers, and then when it loses even one electron, it almost loses 100 picometers, so gets a lot tighter. Okay, so the ionization energy, the definition, energy necessary to remove an electron from an atom. So if you have high ionization energy, then it is not easy to remove an electron. So energy necessary is not good. So some of this you can even think of and apply what you already know. So you would know that metals lose electrons and nonmetals gain electrons. So if you think about it, even to say this, it's not easy to remove an electron, we wouldn't even think of nonmetals losing electrons. We think of them gaining. So they're going to have super high ionization energy. So in your assignment, the peaks of the ionization energy graph should be noble gases. And noble gases, we don't say they react at all. So their ionization energy should be much, much higher than the rest of the elements in their period. So metals tend to lose. They have a low ionization energy. Non-metals gain. They have a high amount. So sometimes, I always say, try not to push out of your brain things you already know, because you can even if you forget what this means-ish, you can kind of think about what it should be. So the nonmetals are on the right-hand side of the periodic table. So on the right-hand side is going to be the highest ionization energy. So your peaks should have been the noble gases, neon, or I mean helium, neon, argon. And then the metals, which are on this side, so the alkali metals are the um, lowest in ionization energy, which means it's the easiest to remove their electrons. So this little sheet, we're going to watch a video, and you'll see why we have to watch the video. The alkali metals are so reactive that we can't, they have to be stored in oil. You can't even, they'll react with the moisture in the air. Maybe you've watched a video already where they put a chunk of sodium like in a lake or river, the huge explosion it makes. So alkali metals, which are group number 1, are so reactive because they only have one valence electron. So a lot of the properties kind of go together. It's easy to remove an electron. So when you go across, it's going to increase because, again, you've got more protons, makes the atom smaller, harder to remove electrons. So if electrons are closer to the nucleus, then they are more attracted and harder to lose. And then shielding effect, again, you're going to see this last one for across every single time. And when we do down, it'll talk about that the number of shells and the shielding effect is more important than the nuclear charge. You'll see that third one will be the same every single trend. So we have the same shells, so you're just looking at how close are the electrons to the nucleus. So atomic size or atomic radius is the first one we start with because they all kind of relate to that too. The atomic, if an atom is small, then it's harder to get electrons off. If an atom is big, then it's easier. So as you go down, it's going to, the ionization energy is going to decrease. It's going to be easier. The energy required is smaller. It's easier to get rid of an electron because they are farther from the nucleus. So this is connected to the other one. It does say radius increases. If you want to add, if you want to emphasize to yourself, the radius increases because there are more shells as you go down. That's why. It's up to you. That's in the other one, but if you want to add that in there, you can. Okay, so electron affinity is usually the one that students like the least. And the good news is it's also the one that we talk about the least. Okay, so we're going to use electronegativity, which is the next trend, to talk about bonding, ionization energy, atomic radius. They kind of nicely go together. Electron affinity, the definition for it is a little bit weird, but it sort of relates to the word affinity, which really kind of means, you know, a tendency to be attracted to. So this time it's the energy released when an electron is added. So if energy is released, that's good. So again, you can think of it in terms of what you would already know. We would think of nonmetals as gaining electrons. So another way you could think of that is that they have an affinity. The electrons are attracted to them. So, but the other wording here, the energy releasing, is sometimes the part where it gets which is a little bit of a different way to think about it. So if metals tend to gain electrons, then they are going to release a lot of energy when an electron is added. We wouldn't even consider metals to gain electrons, so it makes sense then that their energy released or their electron affinity is going to be very small. So the trend is similar to ionization energy. Because the definition is different. One is energy required, the other one is energy released. So when you go across, no, what is this? Yes, across, then the electron affinity increases because you have smaller atoms. Nuclear charge increases. The size is smaller, making it more attracted. Still, same field. Oh, and if you look at the next slide's all filled in, so it's good. Basically the words that I just said. So when you have a bigger nuclear charge or bigger number of protons, then the electrons are more attracted and the atom gets smaller. You could even, to be super fancy, the atom is going to pull electrons to it greater, which makes sense. You would know that. You would think nonmetals gain electrons. So more energy is given off, so energy being released is good in science. So when a smaller atom with more protons receives an electron. So when we try to make a summary for these trends, I'm going to talk about F for fun, okay? So fluorine is the smallest, most reactive nonmetal, and you can think of it because it's the farthest up and the farthest to the right. Of course, we have to ignore the noble gases for some of these trends because they have a full shell. And then the most reactive nonmetal is francium down here because it's the biggest and it has the lowest ionization energy. So F for fun. Okay, so that is one of the ways you can summarize or think of a summary for these trends. So then when you go down, you're going to have a decrease in electron affinity. Electrons are not going to be as attracted to these nuclei because the atoms get bigger. You have more shells, the outer electrons are farther away, and they can't feel the positive pull of the nucleus. Oh, and there's F for fun right here. So this is just showing fluorine, when it gains an electron, gives off the greatest amount of energy. Okay, so the next trend is called electronegativity, and we, as chemists, electronegativity is very useful for us. Again, we're trying to move towards being more quantitative in determining what's going on with atoms. So one of the things we're going to do is actually calculate what kind of bond exists between atoms. So last year, you should have talked about ionic compounds, metals and nonmetals. Covalent bonds or molecular compounds have only nonmetals. Now we are going to look at a way you can mathematically figure out what kind of bond exists. So the electronegativity values is a numerical value given to represent how greedy an atom is for an electron. So this is the fancy definition. The tendency of an atom to pull electrons toward it in a chemical bond, but often thought of simply as electron greedy. So this trend is very similar to electron affinity. So the trends are the same for the same reasons. If you have a small atom that has a high proton number or nuclear charge, it is going to be more attractive for electrons to go to it in a chemical bond. So we're going to even distinguish between what kind of covalent bond between nonmetals exists. Is there equal sharing? Is there unequal sharing? And then ionic is really a huge, bigger difference between electronegativity values. So again, giving kind of a quantitative side to figuring out what kind of bond there is. So it goes, the electronegativity increases across a period and decreases going down. And the values were calculated by Linus Pauling. So the table on your periodic table says Pauling's electronegativity values. That's just giving, props to him. It doesn't really matter. If you'll notice, sometimes you'll find electronegativity tables that have values listed as 0 for noble gases. Sometimes it's given as a dash, like it doesn't even exist. The table I've provided for you doesn't even have a column with noble gases at all. So because they don't bond naturally, so then they are not going to have a tendency to um, pull electrons towards it, or their tendency is non-existent at 0. Okay, so you'll see variations of that. And then of course the most electronegative element, F for fun, is fluorine. Okay, so again, if you like tricks or whatever to help summarize, then that's one of them. And then francium is the lowest. The good news is with electronegativity, if that's a question on a test, you guys always get this. So you can't even use the information you're given to help you relate it to the other ones as well, because the trend for electron affinity is the same, so it'll increase in the same directions. So you can use that to help you, because you never have to memorize these values. That's not a thing, okay? Reactivity is the one that requires a little bit more of a division. So when you talk about reactivity, you usually compare metals or nonmetals. You wouldn't compare a reactive metal to a reactive nonmetal, because because they lose or gain electrons, then their reactivity is a little bit different. So it has to do with how many electrons have to be transferred. So a smaller number gained or a smaller number lost has the same sort of trend. And so when you put atoms that are very reactive together, then you're going to get a really vigorous reaction or really big reaction. So there's always going to be a distinction, and it's super ruthless. I would never say which is more reactive, sodium or fluorine. That's a ruthless thing to do, because they both have to transfer one electron, and that can be tougher to do. Okay, so larger metals, their valence electrons are far away from the nucleus, easy to lose. Smaller nonmetals, more attracted to the nucleus, better to gain. And then the smaller a nonmetal is, the more reactive it is. Again, their nucleus is more attractive for electrons. Oh, here's that one. I don't think that's on your note if you want to write it down. And then there should be a little periodic table there. We're going to make a summary. So this is where I said you need 6 colors. You don't have to have 6 colors, but it will help. And what I'm going to do, I'll show you what I want the final product to look like. So then you've got a bit of space there. You can put your legend at the bottom if you want, that kind of thing. And the more practice with trends is the little half sheet, this one. And the solutions for that are on the back. Okay, so you can check your work. I do have some plastic rulers, so if you need a ruler, I can sanitize them after. You can come borrow one. If you have a calculator or whatever, we're just going to make straight lines. You don't have to measure anything. Okay, so this is what I want to do, okay? We're gonna draw some arrows, different colors, okay? That's our final product. But we're gonna do it together. So you guys have this. I don't know why it's off to the side. Usually we tend to put them on the left. I don't know why. So that's the reason why it's sort of skewed like that. But we're gonna do 6 because we did 6 trends. And in the note they're numbered, so I'll number them the same way. Like 1 was numbered atomic radius. So pick a color. You guys have a lot of space at the bottom if you want to make your legend at the bottom. I'll do mine over here. So atomic radius is the weird trend. For the other trends, except reactivity, I'm going to draw the arrows with like the arrowhead in the same direction, but atomic radius is opposite. So again, if you're the kind of person who likes to look for patterns as a way to remember, they all go one way, except atomic radius goes the other way. Okay, so that is one thing you can do. Atomic radius also is hopefully, if you don't push out of your brain things you already know, then it would make sense. Yes, when I go down, I know in my Bohr-Rutherford diagrams, it was like row 1, 1 shell, row 2, 2 shells, right? So it automatically gets bigger. So try not to discredit what you already know. Okay, so it increases this way and this way. For size of ions, we don't even actually really need arrows. And what you can do is just kind of quickly make a staircase. To be honest, it really doesn't even need to be perfect, okay? And then this side, these are metals. And because there are less nonmetals, sometimes we use the symbol NM because chemists are lazy, we live short forms. To be honest, the staircase is also one of those things where, depending on the version of the periodic table you look at, sometimes it's in a different spot, so be generous. Okay, so now when we do size of ions, because metals lose, they're going to get smaller. And because nonmetals gain, they get bigger. Not even going to write a nice sentence. Nonmetals, bigger. That's it. Or larger, if you prefer larger, that's fine. What do we do next? Ionization energy. So now ionization energy, electron affinity, and electronegativity, which have to do with something about electrons, losing them, energy release when they're gained, how greedy is something for an electron. They all have the same pattern. So the energy required to remove an electron is going to increase as you go up for an opposite reason that this increases, right? Because you get bigger atoms, it's easier to lose down here and harder to lose up here. Okay, so the next three will all be increase up and over. Also, by the way, I am never going to ask you to reproduce this. This is just a way to help you recognize the patterns. If you're thinking in your head, she's crazy that I'm never going to look at this again, that's okay. There are other ways to do this. All the time, yeah. Okay, so reactivity, we have to draw some strange arrows, okay? Because we have to differentiate between metals and nonmetals. And like I said, I would never make you compare a metal that's really reactive and a nonmetal. So when you do even ionic charge, it goes +1, +2, +3, and then it goes -1, -2, -3, -2, -1, like they kind of go opposite. So this column and this column, in terms of reactivity, can sort of be thought of in the same way, right? They need to lose or gain the same number of electrons. So when you do reactivity, you'll either compare metals or compare nonmetals, okay? So we're going to draw some wacky arrows. So, um, so for reactivity, the bigger they are, the more reactive they are for metals. So I can draw this one here. And bigger is this way. So kind of stop it wherever your staircase is, okay? And then non-metals, it's opposite. You want the smaller ones. So try to sneak in an arrow. You could do it down here. That's sort of weird. Yeah. We'll do it. And this way. Okay, so if this helps you, great. If you hate this, then never look at it again, okay? This worksheet has questions about trends. The textbook ones are also different. If you look at the review, there are quite a bit of questions about trends, but really it's only because there's a lot of different ways to ask the question, and sometimes the more different types of questions you do, the better a topic seems to be.